Now, Chapter 22, Electrochemistry, we now get to the quantitative aspects of such. In the main, there are two types of general calculations which electrochemists do. Application of Faraday's law, application of the Nernst equation. Faraday's law applies to the operation of a voltaic cell run in reverse, an electrolysis or electrolytic cell, where what you're doing is regenerating the anode and cathode materials, running a battery in reverse. The Nernst equation allows us, for a particular electrochemical cell, after we determine E0 for such, to determine E, the actual operating potential for the cell, which of course means, as we'll see when we look at the Nernst equation, that you have to know the composition of the cell system. Just like in doing analysis of equilibrium systems for acid-base reactions and the like. You always got to pay attention to inventory. Now, a couple of comments on Faraday's law. For the most part, Faraday's law calculations are little more than plug and chug. Here's Faraday's law. We give this to you on the information sheet. I don't expect you to memorize it. I don't expect you to derive it, but I do expect you to be able to use it. But to support that, we give it to you. In Faraday's law, Q represents charge. Electric charge has the unit coulombs, and the unit coulombs is a combination of the units amperes for current and seconds for duration of time for which the current has been passed. Fancy squiggle M is formula mass, grams per mole for the material in question. Capital F represents the Faraday's constant, which is the total charge borne by a mole of electrons, 96,500 coulombs. Now that's a lot of charge, but then I trust you remember that a mole of electrons is one hell of a bunch of electrons, and Avogadro's number of electrons. And N is moles of electrons transferred. You can only get moles of electrons transferred by paying attention to the electrolysis process that's being considered. And rather than taking Faraday's law when you are to use it and just try to plug in numbers, understand this thing, what it means from a dimensional analysis standpoint. If you do that, doing Faraday's law calculations are simple. You put together a setup which, by dimensional analysis, shows you that the setup you've written generates the unit or units that the statement of the question or problem requires that you get. This is a virtual guarantee that you will then do the calculation correctly. But if the setup you write doesn't give the units you're looking for, I don't care what numbers you deal with. The calculation you do can't be right. There's a couple of examples given. A comment or two about these examples. The first is about running an electric current through a silver nitrate solution with the intention of plating silver metal on the cathode. The question ultimately is, by passing the current indicated with the amperage cited for the time that the current is to be passed, how much silver metal can be plated? Well, this question is saying, calculate a mass of silver. And where for a chemical substance can you always get a handle on mass of the substance? For any chemical substance. From what property of the substance do you always have information which tells you about mass of the substance? It's formula mass. So, to do this calculation, you're going to have to get out your periodic table and look at the formula mass for silver, which, if my memory is right, is 107.9 grams per mole. We got a periodic table for your use that, unlike this table, does have formula mass information in it. The table that I refer to is in the notes. Next sample problem is about a zinc battery. A zinc battery which is to deliver a particular current. The value for the current is cited in the statement of this example. And we are to imagine that the battery is constructed from a 2.5 gram sample of zinc. Now, in the operation of this battery, what's going to happen is that zinc will be oxidized to zinc plus 2. You familiar with any common batteries that use zinc as one of the operating materials? Just curious. You ever see or use a dry cell? Dry cell? About like this here, size-wise. I think dry cells are usually 6-volt cells. They use zinc as one of the electrode materials. For this question, you're making a battery from zinc. It's supposed to deliver a particular current, and the battery's fabricated from a 2.5 gram sample of zinc. How long can the battery last? Time. How long can the battery last? So, what you need to realize, dimensionally speaking, is that to wrestle with this question, as the sample shows you in the notes, you need the Faraday's constant, because it's got time factor in it, seconds in the numerator. So with that, we'll jump into some problems. Question 2218 is in reference to this zinc battery. Question 2218 says, let's imagine that instead of making this battery from zinc, we make it from aluminum. But we want this battery made from aluminum to last just as long as the zinc battery, same lifetime, and to deliver the same current. What quantity of aluminum will be required to make the aluminum battery rather than the zinc battery? Well, if you think about it, all you need to do is to recognize the difference in electricity liberated by the oxidation of aluminum compared to the oxidation of zinc. Zinc, on being oxidized, develops only one common positive oxidation state. What is it? Plus 2. Aluminum, on being oxidized, develops only one oxidation state. What is it? Plus 3. So, that's really the only thing you have to pay attention to, because that's the only factor that's different from this question relative to the zinc battery, because the battery is supposed to deliver the same current, they're supposed to have the same lifetime. So, how much aluminum? Well, we can answer how much with moles, or we can answer how much with mass. I'll take moles straight away. Then if we want, we can turn it into mass, or how many grams of aluminum. 1 mole of aluminum per 3 moles of electrons. So right off the bat, the first factor that I have written down has got to be the correct way to start to write the setup to answer this question. Because this question says, how much aluminum? How much? Mass or moles? So I'm starting with moles. If I wanted mass, I would have started with formula mass for aluminum. 1 mole of aluminum per 3 moles electrons. The rest of it, in rest of the setup I mean, is pay attention to units. 2 moles of electrons per mole of zinc. We write the factor for 2 moles of electrons per mole of zinc like this, not moles of zinc per 2 moles of electrons, because look what a mess we'd have unit-wise. Then you'd have moles of aluminum times moles of zinc. What the hell would that mean? And in the denominator, you'd have moles of electrons squared. This is nonsense. But this way, we've now immediately established a relationship, an electric relationship between moles of aluminum and moles of zinc, which we have to do because that's what this question asked us to do. Now, the quantity of zinc that the battery was built from was 2.5 grams. But I here have a relationship of moles of aluminum to moles of zinc. So I've got to, as I extend my setup, as I continue to write my setup, I've got to put in a factor here which relates moles of zinc to mass of zinc. Formula mass of zinc. Inverted. So that moles of zinc denominator and moles of zinc numerator cancel. And now, by simply multiplying by the quantity of zinc from which the battery originally described was manufactured, I have calculated a mole quantity of aluminum, which is electrochemically equivalent to 2.5 grams of zinc. There it is. And if I want mass of aluminum, just multiply this by the formula mass of aluminum, which is 27.0 grams per mole. That'll give you 0.688 grams of aluminum. Question 19. Question 19 says, let us consider the electrolysis of a molten metal chloride. The formula for the chloride is MCl3. So right off the bat, to wrestle with this, you're expected to recognize that in a material like this, a metal chloride, the oxidation state of chlorine is -1. You know this. The only negative oxidation state which any of the 7A atoms develop is -1. That means the oxidation state for the metal is +3. Here is the reaction that will take place when you run this electrolysis. You're going to plate the metal at the cathode, and at the anode you're going to turn chloride ion into chlorine. And this statement shows us that to make a mole of this metal, per mole of metal made, you have to supply 3 moles of electricity. Again, because the oxidation state of the metal in the metal chloride is +3. So how can we identify this metal? Since that's what the task is described by this question. Well, calculate its formula mass. And then we'll get out our periodic table and see which metal has this formula mass. Now, the question goes on to say that in running this electrolysis with a particular current for a certain amount of time, we are producing 2.695 grams of the metal at the cathode. Well, if I want to calculate formula mass, the first thing I'm going to write down is 2.695 grams of metal, because I want to establish a ratio of grams of metal to moles of metal. That's the formula mass. The setup I write has got to give me, unit-wise, grams of metal per mole of metal. So I write this first. Then I take advantage of what I recognized up here. 3 moles of electrons per mole of metal. Now I have what I want to answer the question. Mass of metal in grams per mole of metal. So if I can get the rest of these units to disappear and write a setup that involves the data which is supplied in the statement of this question, I got it. Well, how can I, unit-wise, remove moles of electricity? I multiply by the Faraday's constant. 96,500 amp seconds per moles of electricity. So moles of electricity disappear. Now when I look at the Faraday's constant, the part that remains unit-wise is amps in the numerator and time in seconds in the numerator. The current used to run this electrolysis was 10.0 amps. What do I do with this 10.0 amps? Multiply or divide? Well, I got to get rid of the unit amps, so I got to divide by the amperage. And amps goes away. Now unit-wise, I got mass of the metal in grams per mole of the metal, which is what I want, times 96,500 and the rest of this stuff factored in with the unit in the numerator time. So I got to get rid of time. So I got to divide by the duration of time for which this electrolysis was conducted. It's 25 minutes. Well, this is in seconds. I think we can all easily establish a relationship between time in seconds and time in minutes. That's what I wrote. And now when you do the arithmetic, your setup tells you you get the units you want, grams of the metal per mole of the metal. The 3 sig figs, I get 52.0, and if you get out the periodic table, you'll find out the metal is chromium. Question 20. Question 20 is really rather like what we did over here with question 18 when we related the aluminum fabricated battery to the zinc fabricated battery. Now we're going to imagine, relative to question 19, that we're going to electrolyze magnesium chloride rather than what we've now determined to be chromium chloride. If we electrolyze molten magnesium chloride with the same current for the same duration of time, 25 minutes, 10 amp current, how many moles of magnesium will we make relative to moles of chromium which we produced? Question 19. To answer this question, do we need to pay attention to the 2.7 grams of chromium that we produced? That's 2.695 to 2 sig fig. Rather than electrolyzing molten chromium chloride with chromium in the +3 oxidation state, we're now going to electrolyze molten magnesium chloride. We're going to do the electrolysis with the same current for the same amount of time. Will this give us more moles of magnesium than moles of chromium produced? The same moles as moles of chromium produced, or fewer moles of magnesium relative to moles of chromium produced? What property of magnesium do we have to pay attention to answer this question? This is the chemistry part.
Oxidation state.
Oxidation state. Magnesium only develops one oxidation state in its chemistry. What is it? +2. And that, of course, is told us by the formula for magnesium chloride. This formula tells us that by electrolysis, when we want to make a mole of magnesium, we got to give 2 moles of electrons to every mole of magnesium ion that we want to reduce. Nothing fancy about this. Well, tell me, I'm using a particular current for the same amount of time as question 19. Does it cost me more electricity or less electricity to make a mole of chromium compared to making a mole of magnesium? Costs you more to make the mole of chromium, right? You got to pump in 3 moles of electricity to make a mole of chromium by this process, but only 2 moles of chromium, 2 moles of electrons to make a mole of magnesium. Well then, by this electrolysis, are we going to make more moles of magnesium or fewer moles of magnesium compared to moles of chromium? More. Enough said. By what factor? How many more moles of magnesium will we make relative to moles of chromium? What is the factor? 1.5. 3/2, right? 3 moles of electricity to make the mole of chromium, 2 moles of electricity to make the mole of magnesium. So if you figured out, if you wanted to know exactly the number of moles of magnesium produced, you'd figure out how many moles of magnesium you have in this sample of, you'd figure out how many moles of chromium you have in this sample of chromium which you produced by using its formula mass, and multiply by 3/2. That's how many moles of magnesium you'd make. Now, what about mass of magnesium compared to 2.7 grams to 2 sig figs? By this electrolysis, we made 2.7 grams of chromium. We know we're going to make more magnesium, right? 1.5 times as much moles, or as many moles. Will this sample of magnesium we produce weigh more, weigh less, or weigh the same as 2.7 grams? Do we have to do any fancy arithmetic to answer this question? What property of magnesium do we have to pay attention to answer this question? Formula mass of magnesium. Anybody know the formula mass of magnesium? You can look it up in the notes. You got the periodic table in there. It's 24.3 grams per mole. We'll write that down. And by this calculation that we did to answer question 19, formula mass chromium is here written. How do the formula masses of these two metals compare? Formula mass of chromium is more than double the formula mass of magnesium, isn't it? Now I go back to the question. If by this electrolysis process I made 2.7 grams of chromium, will I make a sample of magnesium that weighs more or less than 2.7 grams? I'm making 1.5 times more moles.
Less.
But how many grams will I make relative to 2.7? More or less?
Less.
Less. Is there anything difficult about it? You realize I made 3/2 moles of magnesium compared to moles of chromium, right? Okay. But a mole of chromium has a mass of 52 grams. 2 moles of magnesium, 2 moles of magnesium has a mass that's less than 52 grams. Well, I didn't make 2 moles of magnesium. I only made 1.5 moles of magnesium compared to moles of chromium prepared. I got to make well over 2 moles of magnesium to have a sample mass which exceeds 2.7 grams. The ratio of the formula masses tells us this. And one of the reasons why I do this stuff relates to what I've told you folks previously. You need to sharpen up your numbers thinking. Because that stuff, for many of you, I'm sorry to say, was taken away by lousy math teaching in high school or wherever you came from. When students are asked to divide 35 by 7, and they immediately say 5, and asked to divide 3.5 by 7 in short circuit, something's wrong. There's something wrong. But I know damn well that a lot of today's students, if I ask 35 divided by 7, they'll say 5. Then I say 3.5 divided by 7, and they short circuit. You don't do that. 10 to the minus 2 times 10 cubed. Where's my calculator? Baloney. Don't do do that. Don't do that. You got the greatest computer you'll ever have right here. Use it. Now, enough on Faraday's law. Again, it's not much more than plug and chug, provided you pay attention to units. If you pay attention to units, Faraday's law calculations are easy. And if you don't pay attention to units, Faraday's law calculations are going to be very difficult, because you're going to rely on the use the formula and shove in the data method. And by that method, students often ask the calculator to do the wrong arithmetic. Probably I've told you before. I've had students come to me with the calculator in hand and announcing, the value I just gave you has got to be right because here it is on my calculator. And I tell them, the calculator gets an A, but you get a flunk. Because you told the calculator to do the wrong damn arithmetic. It did what you told it to do, but you didn't tell it what to do. All right, Nernst equation. There's a lot of discussion in the notes about the Nernst equation and its applications, because the Nernst equation has a whole lot of applications. Its primary use, or perhaps I should back off on that because I don't know for sure if it's its primary use, but I know that it's one of its primary uses, is to calculate equilibrium constants. Equilibrium constants are commonly determined by electrochemical measurement. You'll see in a few more moments, that with the Nernst equation, you can take every one of those half reactions that you see in our half reaction table, and after you couple them up to make a net cell reaction, for any net cell reaction you generate, and we've already recognized with this list of half reactions, which is not an extensive list, but it's over 40. So you can write one hell of a lot of redox reactions from that list. And with the Nernst equation, you can calculate a K value for every one of these redox reactions. And what you're going to find out is that the K values for redox reactions calculated under standard state conditions are usually damn big numbers. What's that mean? That means redox reactions, practically speaking, are one-way streets. That means if I put together a mixture of zinc metal and zinc ion and copper ion, the only reaction that's going to take place is zinc reducing copper ion. You're not going to get any copper reducing zinc ion. Unlike acid-base reactions, for example, or reactions which involve semi-soluble salts in their dissolving, or complex ions in their decomposition or formation. A lot of those reactions have K values that are close to 1. From an extent standpoint, what kind of extent are we talking about for a reaction that has a K value of 1? We've done this before. What kind of extent are we talking about for a reaction that has a K value of 1? What kind of extent? Pardon? I want a number.
Greater than 50%.
What is it?
Greater than 50%.
Greater than 50%. No. 100%? Oh no, nowhere near. It's not greater than 50%. And it's not less than 50%. What is it? It's 50%. Nernst equation. Again, the derivation is in the notes. We're not responsible for the derivation. It comes from these two fundamental Thermodynamic relationships for electrochemical processes. The Nernst equation written in its most common form is this, where the operating potential for the cell is shown to be the standard operating potential for the cell, less 0.059, you can take this to more significant figures, but 2's enough, times V volts, potential, the units for E and E0 values, divided by N. N is moles of electricity. Transferred, just like in the Faraday equation. And comes from the equation for the reaction. The only way you can get in. Q in this case, remember for our Faraday's equation, Q is representing charge in coulombs. Not this Q. This is our reaction quotient Q, which has the same form as the equilibrium constant. So a couple questions before we start doing some sample Nernst equation calculations. When Q is equal to 1, what's the value for E cell? When Q is equal to 1, what's the value for E cell? I heard a 0. That's not right. When Q is equal to 1, what kind of conditions are we operating under? Oh no. When Q is equal to 1, what kind of conditions are we operating under? We did this in chapter 22. Pardon me, chapter 21. What kind of conditions? I'm listening. All the terms in Q, each term in Q is 1. That means molar concentrations are 1. Gas partial pressures are 1. What kind of conditions? Standard state. What's a log of 1? So I go back to my question. What's the value for E cell when Q is equal to 1? It's the standard state operating potential, isn't it? Because we're under standard state conditions. What if Q is equal to K? And this K is not temperature. What is this K? What is it? What is this K? What is it? You've seen it a bazillion times. What is it? It's the equilibrium constant. So now all the values in Q are equilibrium values. All the values in Q are equilibrium values. So what's E cell? What's E cell? 0. Things at equilibrium. You're not getting any usable energy out of a system at equilibrium. Delta G 0. So, let's go to question 21. With question 21, we're going to revisit the first electrochemical system we looked at when we started into chapter 22. I'll write it in standard cell notation, which you talked about during discussion class, to see, after I write this cell in standard cell notation, see if you recognize it. Does this look familiar? Do you recall from a demonstration standpoint? I had a strip of copper and a strip of zinc, and 1 molar copper sulfate solution and 1 molar zinc sulfate solution. And the first thing we did was to put a zinc bar in the copper sulfate solution and a copper bar in the zinc sulfate solution, and found out that on the surface of the zinc bar immediately deposition of copper metal took place. Whereas on the surface of the copper bar standing in the zinc sulfate solution, nothing happened. If we let it stand there forever, nothing would happen. The result of which we recognized was that zinc is a stronger reducer than copper, which means hydrated copper ion is a stronger oxidizer than hydrated zinc ion. So if we were going to put zinc and copper in our half reaction table, and hydrated copper ion and hydrated zinc ion, we'd have zinc over here on top of copper because we are writing the reducers in order of increasing strength from bottom to top. And then in our oxidizer column, we'd have the respective conjugate oxidizers of these metals arranged in this fashion. Because just like with acids and bases, if the acids are getting stronger in the acid column from bottom to top, then the base has got to be getting stronger in the base column from top to bottom. So if the reducers are getting stronger in our reducer column from bottom to top, then the conjugate oxidizers of these reducers, this for this, this for this, got to be getting stronger from top to bottom. If this is a stronger reducer than this, that means that this can reduce this oxidizer, and this reducer cannot reduce this oxidizer. Not unless we push electricity in there and make it happen. Because this is a better oxidizer than this. And this is a better reducer than this. All right? Secondly, when we express a cell in standard cell notation, as we have here, the standard electrochemical practice, or practice of electrochemists, is to read the cell expressed in standard cell notation from the anode and the chemistry that takes place in the anode half cell to the cathode, and the chemistry that takes place in the cathode half cell. This statement, as it is written, means that we got a half cell called the anode, in which zinc is being oxidized to hydrated zinc ion. The vertical line, single vertical line, is a phase separator. This is solid, this is liquid. Different phases. The double vertical line means what? That's a symbolic representation of the gadget we use to interconnect the half cells. By demonstration, what gadget did we use to interconnect the half cells? A salt bridge. This is the formula for the stuff that's in the cathode half cell and which is getting reduced. Hydrated copper ion. When hydrated copper ion is reduced, it becomes copper. And this occurs at the cathode. So if we use copper as the cathode material, then we need not write anything more for this electrochemical cell. Because we've got the anode material, which is the stuff getting oxidized, the oxidation product, the oxidizer, the stuff that gets reduced, the reduction product, which for this case is the same as the cathode material. Okay so far? Now, we know for this electrochemical system, E0 cell is 1.10 volts. Again, if you want, we wrote this on the board when we looked at this system, but if you want, you can look in the half reaction table and you'll see as zinc converts to hydrated zinc ion with the liberation of 2 moles of electricity per mole of zinc oxidized, E0 is plus 0.763 volts. And for copper, being oxidized to hydrated copper ion, as 2 moles of electricity are produced, E0 is minus 0.34 volts. What I'm doing now is to cite to you these half reactions as they are written in the half reaction table with the corresponding E0 values. But in coupling, to build us an electrochemical cell which will in fact function to give us usable electrical energy, we have to take the half reaction of lower E0 and turn it around, because that half reaction contains the poorer reducer and the stronger oxidizer. Put another way, which is what this notation tells us. When I consider the two half reactions, zinc becoming hydrated zinc ion and copper becoming hydrated copper ion, if I recognize that zinc is the stronger reducer than copper, then I know hydrated copper ion can readily oxidize zinc, whereas hydrated zinc ion isn't going to oxidize copper at all. Not from a naturally occurring standpoint. So it's the copper-copper ion half cell, which I write in the opposite direction, and in so doing change the sign on E0. So now it's plus 0.34 volts. And when I add that to plus 0.763 volts, that's what I get. So for this electrochemical system, let's now write the Nernst equation. There's E0 cell. Down here is N. What's the value for N? You got enough information on the board to tell you the value for N? What is it? As a mole of zinc becomes a mole of this ion, how many moles of electrons must be liberated? 2. 0 oxidation state plus 2 oxidation state. And as this process takes place, what gobbles up these liberated electrons? This stuff. And for a mole of this stuff to become a mole of this stuff, how many moles of electrons must be consumed? 2. So there's that. Now what's Q? You can write Q from what we got on the board. If you write the net cell reaction, can you see it in your mind's eye? Zinc plus hydrated copper ion, reaction arrow. Products, hydrated zinc ion and copper. Which terms in this reaction equation appear in Q? Zinc metal? No. Copper metal? No. Hydrated copper ion? You betcha. Numerator or denominator? Numerator or denominator? Is hydrated copper ion a reactant or product in this reaction? Reactant. So where does copper ion appear in Q? Denominator. Correspondingly, hydrated zinc ion is a product. So that's in the numerator of Q. Now, I've given you here 4 solutions. 2 of which contain hydrated zinc ion, 2 of which contain hydrated copper ion, each of which contains sulfate ion, which is an ion which will not be part of the chemistry in this system. If it was, we'd have to tell you, or give you some information which will allow you to determine such. To make this cell operate so as to deliver the greatest quantity of usable electrical energy, which means make this cell operate so it has the largest value for E cell. Which of these solutions do you wish to use? And how will you use these solutions? In other words, will they be placed in the anode half-cell compartment or the cathode half-cell compartment? There's your choices. Which solutions do you use, and in which cell compartment are they to be placed? There's a zinc bar. It's sticking in a solution. A solution which you're now going to decide on. There's a copper bar. Sticking in a solution. A solution you're now going to decide on. Zinc's our anode. Copper's our cathode. We'll solder a piece of wire from the zinc anode bar to the copper cathode bar. And in here I'm going to put a socket so I can screw in my light bulb. I want my light bulb to light up and be as bright as it can be. Here's my salt bridge. This, of course, is the anode half cell. This is the copper cathode half cell. Cathode half cell. Which solutions you grabbing? And where are you going to put them? Well, let's have some fun and go down the list. 1 molar zinc sulfate solution. How many will use this solution in assembling this electrochemical system? I want hands up if you want to pick this solution. No looking around except me. I run this election. If there's any cheating, I do it. Hands up. I want to count the number of hands of voting for using this solution. I want to see if you know how to build an electrochemical cell efficiently. And I don't want any half votes. I want to see those hands. Don't put your hand up if you don't want to vote for this one. There's all kinds of stuff going on here. We're oscillating. All right, I'm going to take this as a 0. 0 votes. How many want to use this one? I see 1, a half a vote, a half a vote, a half a vote, and 1 vote. That's 2.5 volts. Votes. Not volts, votes. 1 molar copper sulfate solution. How many want to use this one? 1, 2, 3, 4, 5, 6, 7, 8. 10th molar copper sulfate solution. How many want to use this one? 1, 2, 3, 4, 5, 6, 7. How many only voted for 1 solution? You think you can run this with just 1 solution? You got to have a solution in each half cell container which has got ions in it. Because you got to have ions present to support current flow. So those of you who picked 1 solution are going to build an unusual electrochemical system. You're going to make a half a system. It ain't going to run for half the time. It's going to run for none of the time. All right. 2.5 people. I'm going to watch out for this half a person. This 0.10 molar zinc sulfate solution. Where are you putting it? You can put it in this beaker, or you can put it in this beaker, or you can put it in both beakers. I want to know. You putting it in this beaker only? Hand up. Just this 2.5. I don't want any. Putting it here? No hands. Putting it here? That's nice. You just made a short circuit. No, you didn't. You didn't make any circuit. You made a nothing. You got a copper bar sticking in zinc sulfate solution. Does copper reduce zinc ion? No. Well, that's not doing us any good. Do you remember that in order for an electrochemical system to operate correctly, you must physically separate oxidation from reduction? Remember what we did with our demonstration? When we put the zinc bar in contact with the copper ion and saw the immediate deposition of copper, we said, yeah, we got a redox reaction going on. We got electrons being transferred, but we're not able to harness those electrons. That system does not give us usable electrical energy. It gives us electrical energy, but not anything we can use. That system is known as a short circuit. 1 molar copper sulfate solution. Those of you who voted for this solution, tell me, you want to put it in this beaker? I got 1 vote. You want to put it in this beaker? How many vote for this? I got 4 votes. 5 votes. That's good. So in here we got 1.0 molar copper sulfate solution. We still haven't decided what's over here. Well, we got no votes for this, so I'll scratch this one out. And we'll check this because it's been used. We got 2 solutions remaining. 7 voted for this. All right, of you 7 who voted for this, where do you want to put it? You want to put it in here with the copper sulfate solution? That's 1 molar. You want to put it in here in this beaker. So far there's nothing in this beaker. How many vote put it in this beaker? I got 1 vote. How many vote put it in this beaker? We had 7 people told us they want to use that solution, but now I only got 1 vote. 6 people mysteriously disappeared. Evaporated right before our eyes. You think I have fun with this? You're damn right. But I want you to learn. And in order to learn, you have to think. There's no way around it. If you're in a science class where all the quizzes and exams are run like Jeopardy, the teacher gives you a data point, and on the quiz or exam you give back the data point. That isn't worth a hoot. A 3rd grader can do that, and doesn't have to be a smart 3rd grader at all. We don't want this solution. We want this solution and this solution. Here, we want, for the solutions from which we are asked to choose, 10th molar zinc sulfate solution, and here we want 1 molar copper sulfate solution. So we got a zinc bar, stick it in 10th molar zinc ion, and a copper bar, stick it in 1 molar copper ion. And we now look at our Nernst equation and focus on Q, because up here we have the value 0.10, and down here we have the value 1.0. You see this sign here? This sign tells you that you want Q to be a number which is bigger or smaller than 1 when you want to maximize E cell. Bigger or smaller than 1? Smaller, because you take the log of a number that's smaller than 1, you get a number with what kind of sign? Minus. And minus times a minus means what? Plus! Ha ha! Now E cell's bigger than E zero cell. So, you want the ion which is being produced by oxidation. Product. And that's why it's in the numerator. To be at a smaller molarity than the molarity of the ion which is being reduced. That gives us a Q value which is smaller than 1, and gives us a log term which is minus, and by this gives us a whole term that adds to E0. Notice that if I gave you 0.00010 molar zinc sulfate solution and 6.0 molar copper sulfate solution, I'd write down 100 molar, but I'm sure you can't make it that concentrated. Now if I use these solutions, I'm going to beat the hell out of this cell, because now up top I'd have this, and down here I'd have this, and that's a lot smaller number than what we just had. So now when I play this arithmetic game, I'm going to get a much bigger term to add to E0 cell, and in so doing make E cell all the bigger. Now then, let's play this game further. Let's play this game in accord with what you presumably talked about in discussion class when you looked at this cell. Get out the half reaction table. You'll need it now. I'm going to supply you with some 6 molar ammonia solution. All right? Here's the system as it stands. As things presently stand, zinc is to be oxidized to this as hydrated copper ion is reduced to copper metal. Okay? You're looking at the half reaction table. I'm supplying you with some 6.0 molar ammonia solution. Your task is the same as it was before, to make this electrochemical system operate so as to give us maximum amount of usable electrical energy, which means you want E cell to be as big as it can possibly be. What are you going to do with this 6.0 molar ammonia solution? We're considering the system presently operating with zinc being oxidized to hydrated zinc ion and hydrated copper ion being reduced to copper. I'm going to offer you now use of this 6.0 molar ammonia solution and ask to make E cell go up. Will you add the 6.0 molar ammonia solution to the anode half cell? Will you add the 6.0 molar ammonia solution to the cathode half cell? Will you add the 6.0 molar ammonia solution to both half cells? Or is this system giving us a bigger dose of usable electrical energy than anything we can do with this? So regarding this, to repeat, add to anode half cell only. Add to cathode half cell only. Add to each half cell. Add to neither half cell, because we are believing that this system is giving us a bigger chunk of usable electrical energy than anything we can do with this ammonia. So you got 4 choices. There's the choices. All right? You got your voter's card ready? Huh? Choice 1, add to the anode half cell only. You're looking at the E0 information. How many want to do that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Add the cathode half cell only. 5, 4, 3, 2, 1, 0. Add to both half cells. I see 1 vote. Add to neither half cell, because this system is doing a better job. 1 vote. I'm thinking about it. 1. And so, as it follows from this one consideration, we got 12 A's and everybody else flunks. Look at the E0 information and the corresponding half cells. Look at the half reaction table. I'm going to write 2 new ion formulas on the board. I think these are 4 complex. Let me check to make sure how I wrote these in the notes. Yeah. Question. You see this ion here? Tetramine zinc plus 2 cation. How does the stability of this ion compare to the stability of this ion? Because this list of half cells is really a list of thermodynamic stability information. Which one of these is more stable? Which one? The ammonia complex or the water complex? The ammonia complex is more stable. Now look at the copper complex. Which is more stable? The copper ammonia complex or the copper water complex? Which one is more stable? Look at the half cell information. You've got to be able to read that stuff. A whole bunch of this exam depends on your being able to read that stuff and understand how to use it. Which one is more stable? Which one? Tell me. Look at the half reactions. The E0 value for copper being oxidized in the presence of water to make the hydrated copper ion. That's minus 0.34 volts, right? How about copper being oxidized in the presence of ammonia to make the copper ammonia complex ion? I believe that says 0.05 volts. Minus 0.05 volts. Is that correct? I'm doing this from memory, so I'm asking you. What's it say? Plus 0.05 volts? Okay. So I want to know, which is more stable? The copper ammonia complex ion or the copper water complex ion? Because the data I just told you to look at, the information I just told you to look at, shows you oxidizing copper in the presence of ammonia is a much better, much more thermodynamically favored process than oxidizing copper in the presence of water. Just like oxidizing zinc in the presence of ammonia is a much more thermodynamically favored process compared to oxidizing zinc in the presence of water only. These ammonia complexes are each much more stable than their corresponding water complexes. That tells me if I put ammonia in the anode compartment, now when I oxidize zinc, instead of turning it into the water complex, I'm going to turn it into this complex. What impact does that have on E0 and E cell? Does it make E0 and E cell stay the same, go up, or come down? Up! Because this is a hell of a lot more stable. I'm now turning zinc into something that's a lot more stable than it was before. And this system operates on zinc being oxidized. So I now made zinc more readily oxidized, didn't I? I turned it into a more stable stuff. But if you put ammonia in the cathode compartment, now you made copper ion more stable. You turned it into the ammonia complex. And that's more difficult to reduce because it's more stable than the water complex. You don't want that. You want the stuff that's easiest to reduce. You want the stuff that's the better oxidizer. And the water complex of copper ion is a hell of a lot better oxidizer than the ammonia complex of copper ion because the ammonia complex is much more stable. So here's the system you want. Zinc ammonia complex ion in the numerator and the copper water complex ion in the denominator. That is the best system you can make compared to the water complex ions only or the ammonia complex ions only. Pick it up from this point tomorrow.